Hi everyone, and welcome to the second session of the day about fault attack on post-quantum cryptography. The first talk is going to be about correction fault attacks on randomized crystal dilithium by Elisabeth Kramer, Pisto Persel, Jörg Land, and Tim Guinnessiu. And the speaker is Elisabeth Kramer.
Thank you. Okay, I'm going to talk about correction fault attacks on randomized crystal dilithium, and I realize I'm too small. I can only see half of the screen. This is a joint work together with Peter Pessel from Infineon and Georg Land and Tim Guinnessiu from the Ruhr University in Bochum. The next few minutes, this is the plan. I will start with a very short introduction, and then I go over the two attacks that we present in our paper. And then in the end, I have one conclusion slide. Okay, let's get started. I will not do the 5-minute why do we need post-quantum cryptography and so on. I think everybody agrees. So you also probably all know about the NIST standardization process, and maybe you've also heard that the dilithium, which is a signature scheme, has been turned into a standard. So for a few weeks now, we have actually the standard. It's now called MLDSA. Okay, now if you have not looked at dilithium before, then maybe the next one is a bit new for you. Dilithium comes in two variants, the deterministic and the randomized. The randomized is now in the standard called hedged mode, and it's actually the default. And by the way, I will probably use the dilithium vocabulary during the rest of the talk because we have done that before the standard was published. Okay. I mean, the paper is called Correction Fault Attacks, so it's not a surprise. I'm going to talk about fault injection attacks. We have also not been the first one to look at that. There are a few publications regarding fault injection attacks on dilithium. Some of them target the deterministic variant. They are pretty strong attacks, so I would not advise you to use the deterministic dilithium without any protection. Of course, also some papers regarding attacks on the hedged mode. These attacks are not that strong, and our work falls into this category. And side note maybe, the attacks that target the randomized version generally also work on the deterministic variant, but not the other way around. So let's come to the fun part, the attacks. The first attack that we describe, we called extending the skipping fault attack. So this attack is based on another attack from 2019. So Ravi and co-authors explained this attack for deterministic dilithium, and we show now that you can generalize it, so it doesn't matter which mode of dilithium you use or how it's implemented. So here you can see the dilithium sign function. This is actually now taken from the standard, from MLDSA standard. And don't worry, I'm not going into the details, so at least for my talk, you're safe. I just want to show you the target operation of our attack. So you can see here line 20. I guess it's a bit small, but this is an addition. So in line 20, what happens? And actually, these are two vectors of polynomials. So we're not just adding two numbers, we are adding two vectors of polynomials here. And what we need for the attack to work is it's kind of in the name, we need to skip this addition. However, we do not need to skip the addition in whole. It's sufficient if we actually change just the addition in one of the coefficients in one of the polynomials here. Okay. For this attack, we did not do any experiments because actually they have already been done in the paper from 2019. So how does the attack work? Not surprisingly, we start by getting a faulty signature. So if we inject the fault that I described before, then we will get a signature where the middle part, it's called Z, will be affected. And what we now do is we correct this part Z. Okay? So in the faulty signature, if the fault worked as we wanted it to work, then we will get a Z prime, which is equal to a value Y. For now, it's not important what Y is. I'm just telling you, you get the Y. But for the correct signature, you would need to, or you would receive a Z, which is equal to Y plus C times S1. And what we do now is, well, we are using a brute force search to find the missing part, which is the Z times S1. And we use the verification routine to determine whether we found the right value. If we found it, so if we have added something to the Z prime and the signature then verifies, then we get a linear equation in the coefficients of the secret, S1 in this case. So this is what we want to recover ultimately. This means we're going to repeat that a couple of times, and then we get a linear equation system for the secret that we can then solve. Okay. If you're wondering, yes, there are more parts to the secret key of dilithium, but actually having S1 is enough to forge any signature. Okay. We have implemented the attack. As I already said, we did not do actually the fault injections, but we used simulated faults to, well, show that it works. What we have done is, you can see we have implemented three variants of the attack. So the first one is the basic attack, as I described it a few moments ago. And then what we have also done is we have looked at possible countermeasures that you could come up with to prevent the attack. And we found out that if you would maybe suggest that you could just shuffle the addition, so the target operation, randomly, then we showed that our attack can be modified, so it can bypass this countermeasure. Also, one might suggest to use something like double computation or sign and verify. Also, this can be circumvented by our attack. Okay, so for the basic attack, we can see that we have successfully recovered the secret key in a few seconds. The number of faults here is actually a fixed number, so if you're working with simulated faults, so every fault is successfully injected, then this number only depends on parameters of the lithium, so it will always be the same. For the modification to bypass a shuffled addition, you can see it takes considerably longer. You do need a little bit more faults. However, when it comes to the times that you see here, I have to make a note on that, because this is run on just my laptop. Also, this implementation here is highly non-optimized. So I believe you can go much faster. And when it comes to the modification that can circumvent the double computation or sign and verify, you can see we're back down to seconds. We do, however, need a lot more faults. But yeah, it's possible. And if you were wondering, you cannot combine these two modifications, so they are mutually exclusive. Okay, so that's the first attack that we described, which is, well, an extension of an already existing attack. So now let's come to the second attack, which is not an extension, but it's something new. So this time, the target operation for our fault is actually not in line 20, but in line 5. So you can see here, the operation that we're targeting is you take some seed rho and you expand it into something that's called A, and I'm telling you now, A is a matrix of polynomials. If you have very good eyes, you might see that the A has a hat on it, and that just means that the matrix here, or the polynomials in this matrix, are generated directly in their entity transform. So what do we need for our attack? Well, we need to fault this value A, or hat A. We need to disturb it in one of the coefficients, one of the polynomials. And we also need to know by what value. So we need to know the difference between the faulty value and the correct value. Now you might say this seems to be a very strong requirement. However, and this is what makes the attack so interesting, the operation, the value that we are targeting here is completely public. So rho is actually part of the public key, and everyone who wants to verify a signature needs to be able to do this operation. So that means we always know the correct value in this hat A. For example, and this is what we've done, I will come to that later again, if you achieve something like a Z0 fault, then you automatically know the difference between the faulty and the correct value. Cool, so how do we get the secret key from faults in the public key? I mean, yeah, we start with the faulty signature. This time, however, the fault does affect all parts of the signature. So not only just the Z part, but all parts. But we are not trying to correct the signature itself now. What we are trying to correct is a value that appears during verification. Okay, so here you can see in green, during verification, the most important step is to calculate this value AZ prime minus C prime T. And of course, if you have injected the fault successfully, then this will be not the correct value. However, we know how the correct value needs to look like. So if we add to this AZ prime minus C prime T the value delta A times Y, then this is the correct value for verification, and in this case, the verification routine will conclude successfully. So again, we are enumerating this value that we are looking for, and well, we see when is our verification successful, and then we know with overwhelming probability that we have found actually the correct delta A times Y. If we know that, then, because we know the delta A, we can solve for one coefficient in the entity representation of our secret. So not the secret directly, but the entity version. Which means if we repeat that for all of the coefficients in the entity version of S1, then we can, well, apply the inverse entity and we get the secret again. Here you can actually kind of balance the attack in the following sense. Because of how S1 looks like, you do not need all the coefficient in the entity of S1. So you can get away with a few missing coefficients if you use your favorite lattice reduction algorithm. So if you're willing to spend a little bit more time on the attack, then you do not need as many successful faulty signatures. Okay, so at first we tested it with simulated faults, because obviously if it doesn't work, we do not have to do the experiments. And we can see here, yes, it worked, surprise. For dilithium 5, the attack recovered the secret key successfully in under 10 minutes. Here, however, we did not use my laptop, and we actually did optimize the code. So this time we ran it on a server with 256 threads. The number of faults here, maybe you recognize these numbers because we've seen them before. They are also not changing if you're using simulated faults. So again, they are only dependent on the parameters of the lithium. Okay. And now comes the part where we actually try to experimentally verify this attack. The setup was quite simple. So we used a chip whisperer Lite connected to a chip whisperer UFO and a target chip STM32F405, which ran the optimized PQM4 implementation at the default 24 megahertz. And to achieve the faults that we needed, we used clock glitches. And actually here we did exactly what I hinted at before. So we set the target coefficient to 0. And then we knew the difference to the correct one because, well, we know the public key matrix. Okay, what are the results? We get 30 to 90% successful fault injections, which seems to be a very wide spread. But so what actually happened is that a few coefficients had a very bad success rate. So to be exact, like I think every fourth coefficient was had a really bad success rate, and all the others were around like 80%. Okay, and then the total attack, we only tested it for dilithium 2. You would do exactly the same for 3 or 5, you just have more coefficients. We decided to split the attack into an online part and an offline part. So first we generated all the faulty signatures that we need for the attack. We decided, because, well, we don't have a 100% success rate for the fault injections, we decided to generate 10 faulty signatures per coefficient, which took about 2 hours. Then we recovered most of the coefficients in the NTT version of S1 in about 19 minutes. So basically, we used the 10 faulty signatures that we had, and we had a look when we recovered the same coefficient value twice. Then you can be pretty sure that you have the correct value. For some coefficients, however, this did not work out. Specifically those with a 30% success rate, we always got random values back. So we did the lattice reduction trick, which means we spent like another 20 minutes approximately to recover the whole of the secret with the NTT coefficients that we had at this point. Okay, so let me come to an end. For those of you who had been in their wake-up phase for the last few minutes, this is maybe what you can take away. The addition, so this operation here during dilithium, I mean, it has highly sensitive values, so that's not a surprise, but you need to protect this against fault ejection attacks, no matter which dilithium mode you use. And secondly, it is not sufficient to only protect the secret value during the signature generation, because as we have seen now, you can actually recover the secret key with only faults in the public key. So this is the end. Thank you for your attention, and any questions?
Thanks for the talk. Is there any question?
Could you comment on the attack success probability for the first attack, where you kind of used the results from a previous paper? What would be the rate of success for the fault injection?
So in that case, you also need to consider that so during the lithium, you have a rejection step. So you need to always hit the last iteration of this rejection, which means that you need to, on average, repeat the fault injection like 4 or 5 times.
So the attack timings would be 4 to 5 times longer, effectively?
Yes.
Thanks.
Any other question?
Thank you very much for a very nice presentation. I have a question about the deltas there. So I understand that for the attack, or how it was described, for all the results, they have to be exactly known for the attacker. Did you consider what would happen if, let's say, you would only learn something about the distribution, or because like I'm not 100%. Okay, A is public, but I'm just not like, what would happen if the attacker would not know exactly what's happening, but he would know that he's somehow affecting the distribution of the result?
You cannot use this attack. That's basically
even if he would learn something, but not everything, let's say.
Yes, because you always have the influence of the random Y in there.
Okay, so then essentially not everything would be learned. Okay.
Yeah.
Okay, thank you.
One last question.
Thank you for the presentation. It was really great. And your way of presenting is really amazing. You haven't mentioned any countermeasures for this. Can we secure this or not?
Okay, so I mean, you could do something like, okay, so for the first thing, you could maybe do something like masking, because then you would need to actually skip this addition in all the shares successfully. Also, in the first paper, they suggested to maybe do the addition directly in the entity representation, which might raise other problems, of course. For the second attack, so also, it depends a little how you this expand A, or if you, for example, so for example, if you are thinking about shuffling the matrix or the generation of the matrix, you can actually adapt the attack to this, but it would get very costly very fast.
All right, let's thank the speaker again. The next talk will be about exploiting small norm polynomial multiplication with physical attacks, application to crystal dilithium, by Olivier Bronchin, Melissa Azwawi, Mohamed El Garoui, Joe Srin, and Tobias Schneider. And the speakers is Tobias.
Yeah, thanks. Okay. So in this talk, we're going to present a framework for physical attacks to both side channel and fault, so not only fault, like the session title says. And we target small norm polynomial multiplication as found, for example, in dilithium. So I probably don't need to motivate our contribution too much, given that we've just seen a talk about fault attacks on dilithium. So maybe just from a high level, right? As you probably know, PQC standards are not only coming, they're already here now, including dilithium, which is now called MLDSA. And since there's an official standard, right, all the companies are rushing to kind of implement it on like a wide range of devices. So for embedded devices, there are like a lot of challenges, right? Because the keys are larger, the ciphertext is larger, and so on. But yeah, for embedded devices, you have the added complexity of physical security, right? And for classical crypto, we can create highly secure, highly efficient implementations that are even certified because we have like decades of experience with that. However, for PQC, we're kind of only at the start. And there's still like a long way to go. And to reach kind of like the end of the road, we need to have kind of a thorough and sound understanding of the physical attack surface. So while there are already some attacks, the state of the art on attacks on Dilithium is still not as mature as for like classical crypto. And that's kind of what also our contribution is about. So we present a generic physical attack framework covering both active fault injection attack and passive sidechannel analysis. So here you have like a high-level overview of Dilithium. So this is version 3.1, but our framework also works for MLDSA. And you basically have a message M at the top that you then sign using a secret key consisting of multiple parts, and then you also get a signature consisting of multiple parts. So the signature contains this signature Z that we also had in the previous talk, a challenge C, and then hint H. And our framework aims to recover parts of the secret key, namely S1 and S2, which are sufficient for forgery. So one important aspect of Dilithium, right, that it's based on this fiat Shamir with a board framework. That means during signing, you basically sample a random nonce, derive a challenge, and then try to generate a signature. But during these algorithms, there are like multiple bounce checks, and if one of them fails, you kind of restart the whole process. And what's important for our framework is that you also apply such a bounce check to the signature Z. And that is basically only given out to the attacker as part of a valid signature. So yeah, we have seen like the talk before, right? We're not the first to look at physical attacks on Dilithium, and there have been actually quite some publications. Some of them basically try to extract some information that they then use to kind of reduce the hardness of the cryptographic problem, no? And then break it using lattice reduction. For example, here you see that these publications get some information about the nonce Y. For example, if a coefficient is 0, or if there's like a collision in the polynomial. And the issue with this proposal is that they're quite sensitive to noise. That means that the success rate significantly drops if the recovered information is not like 100% accurate. And that's kind of like the key feature of our contribution. So we have this generalized attack framework for profiled SCA and fault attacks, which is kind of like more resistant to noise and also lack of precision in the measurements. So it's more like applicable also to like hardened implementations where the signal to noise ratio might be low due to the implemented countermeasures. So this is based on like belief propagation and enables quite a large variety of attack scenarios, which we'll see later in the experiments. And our basic idea is that inside Dilithium, you have like a couple of polynomials that have to follow like an exact uniform distribution to ensure black box security. No? So namely, we see here the nonces Y and W0, which have to be uniform to kind of hide the output of the multiplication. So why our framework works for like both cases, like right and left. In the following, we just focus basically on the left case, where that is computed from C times S1 plus Y. So the main idea is that we kind of bias some what we call target polynomials, and that's what we then use to kind of recover information about the secret key. So you see here, that's kind of the target operation. So we have like a long-term secret key S1, which we'll simplify to S in the following slides. And then we have like a challenge C. These are multiplied and both have a small norm. So the output also has a small norm, what we denote as X. So X is basically S times C. So if you're given X and C, which is part of the signature, you can basically just directly solve for the secret key and get it. So that's why Dilithium basically adds this nonce Y to hide this information in the signature. So while y doesn't have such a small norm, it is still bounded, and you actually don't need to compute a model reduction when you're computing z because there's no overflow. So in our attack, we then try to bias the distribution of x and y using some physical attacks, or some fault attacks, some sidechain attacks, and then recover information about S1. So I'm going to start by explaining how we can bias and exploit x. So if you look at x, which is like a vector of polynomials, maybe for simplification, we just look at the recovery of one polynomial of the secret key. No? So if you look at x, and then in particular the first coefficient, x0, you can kind of express it like this. We have like a first term that depends on the first coefficient of the challenge and the first coefficient of the secret key, and then like a sum of other terms. And this sum of other terms we can kind of model like a Gaussian distribution using like the central limit theorem with a mean 0 and a given standard deviation sigma. And then if you look at the mean of x0, we see that it also follows this kind of this distribution, but now the mean depends basically on the challenge and the secret key. And that's what we then exploit in our attack. So you would basically use like a sidechain attack, right, to basically sample this distribution of x0, so you get some information about this distribution, and then kind of compute the mean and then use this to recover the secret key. So note that we say the framework is both for fault and sidechain attacks. We actually don't consider faulting x, no? So only sidechain attacks. Now I will cover how to maybe exploit y. So for accepted signatures, the attacker basically gets z, which is equal to y plus s times c. And there, as I said before, we have to assume that y is uniform to kind of perfectly hide x in the z. And that's fine, like in the black box model, right, where we have like this uniform distribution basically of y. However, we can again use some kind of leakage to recover some information about y, which kind of biases this distribution and makes it like non-uniform. In this case, x is no longer perfectly hidden, and we get some information about x. With this information about x, we can then go back to the previous slide and recover information about the secret key. So for y, we can also consider fault attacks. So for example, imagine we set a certain bit of y to 0, and that basically directly biases the distribution, and we can, again, get information about x. So what we can also do is kind of accumulate this information about multiple traces, multiple faults, and also about multiple coefficients. So basically, we just write it as like this equation system you can see here, where c is known, right? S is a variable we want to recover, and then we have x, where we have like the biases. No? So either via direct leakage on x or via this indirect bias on y, right? So we write this equation, we then solve it, and then we basically got S. So in the paper, we describe how the solving is implemented. So we basically build a graph and then use the solver based on belief propagation. So that's well studied in the SCA context, but it's heuristic. And it also can be quite costly to implement and run it. So in the paper, we also provide some more optimization rules, how to make it more efficient. So one important note maybe is that so far we assumed that everything was happening in kind of the normal domain. However, in a lot of implementation, you would use like the entity, right, to speed things up. And that has some impact on our framework. So y is kind of always sampled in the normal domain, so you can't really avoid that leakage. But for c times s and then the addition of y, you could theoretically do it in entity domain. And then you have like less direct leakage on x that you can exploit. So it makes it a bit harder in our framework, but not impossible. Good. So now that I went over like the framework, let's look at some experiments that we did. So again, these are all like simulations. So we didn't really do any like practical experiments, but this kind of allows us to look at the success rate over various levels of noise. So the first one here is a sidechain attack on accepted signatures. So the attacker knows Z and C and gets the Hamming rate leakage of X and Y. And then we kind of simulated it for a range of different SNR values that as you can see in the legend. And it's kind of noticeable that for like high SNR, we basically just need 4 traces to recover the full key polynomial. But as expected, as we increase the noise, the number of traces kind of increases linearly. No? Then regarding like fault attacks on accepted signatures, again, the attacker knows Z and C and induces a fault with like a certain bias. So in this example, I think we took like one coefficient of Y and then we biased all of the bits towards 0. And then we looked at like different like biases that you can see here. So with 1, the fault is always successful. And then for the lower values, sometimes it's not successful. So we need at least like 256 faulty signatures if like the fault is always successful. And we have like 1 fault per signature. But we can also kind of like trade it. So if we do like 2 faults per signature, we kind of like cut the number in half. And in the extreme case where we basically fault all of the coefficients of Y, for example, to 0, Z would be equal to S times C, and we can directly solve for S. No? So in this case, we just need 1 faulty signature. Okay. So maybe also one new thing that we looked up in the paper is that most previous works kind of focused on attacking or exploiting accepted signatures. And what we did in the paper, we also looked at applying basically the same attacks, but now on rejected signatures. So like these previous iterations that didn't make through all of the bound checks, but were like discarded and then restarted afterwards. So in this case, the attacker doesn't really get C because there's no signature given out. But for now, we assume C is known to the attacker. That might be realistic because C is usually not protected, so it might be easy to recover. And also there are some previous works that looked at how to recover some information about C. So we assume it's known to the attacker. Regarding that, so that's not known to the attacker, but instead the attacker kind of targets the rejection event on that. So let me maybe explain that like basically 2 different approaches how you can implement the bound check on that. So one is called early board that you can see here at the top. So basically you check each coefficient separately of that, and once you get to one that is larger than the bound, you reject the polynomial. And if you implement it like this, you basically leak which of the coefficients is larger than the bound. Alternatively, you can also just check all of the coefficients and only reject at the end. So in this case, you don't leak which coefficient is larger than the bound, only that there is at least one coefficient that is larger. Now, in the black box model, this early abort is perfectly fine, right? So there's also this comment in the reference implementation that basically says it's fine to leak the coefficient which is larger than the bound as long as you don't leak anything else. So for example, if you don't leak the sign of Y, then this rejection probably is basically independent of the secret. However, we have seen before, right, that we can bias the distribution of Y, right, using sidechain and faults. And if we do this, the rejection probability is actually dependent on the secret. So we can exploit it to recover information about the secret key. In this case, using early abort actually gives us, or makes it a lot easier for us, because we know which coefficient to target and which is like the most informative one. Okay, so we tried it with faults on rejected signatures, but it was too inefficient, so we didn't include in the paper. But with sidechain leakage, as you can see here, we're actually able to recover the secret key with early abort. It takes a lot more traces, but it's possible. Without early abort, we ran into like the limits of our evaluation setup. So we had to like reduce the parameters a bit to make it fit. And then it kind of worked, but the SNR that we needed was like extremely high. So it's not really realistic in practice to do. So it seems kind of that using early abort is actually beneficial if you have like physical attacks in your threat model. Then one last thing, we also looked at shuffling. So this was proposed in an earlier version of this paper as like an alternative to masking to make it more cost efficient. And what we found is that you basically increase the attack complexity as expected, no? So linearly in the noise, and you have this added factor of the permutation. But overall, it doesn't provide like sufficient security because you need still less than 1 million traces to kind of recover the key. Good. So maybe to sum up, so we proposed a couple new sidechain and fault attack vectors in our new framework, which is more robust to noise in the measurements. In contrast to like previous work, which was mostly focused on accepted signatures, we demonstrated you can also use rejected signatures to recover the secret key. So here in the table, it's kind of like the summary of our contribution. So in red, you see the variables which are like sensitive, and then with a star, it's an attack that's basically covered by our framework. We also looked at shuffling, which was as proposed in an earlier work. And like based on our experiments, we think it's not sufficient on its own to protect the lithium like sufficiently. So we would all recommend to at least use masking for all of the variables. Regarding future work, so the extension to a framework to combine attacks is rather straightforward because the exploitation step is, but basically doesn't care where the biases come from. So you basically can take the biases from both types of attacks and then just run it to a framework, and then you get the result. And of course, you can, as seen also in the previous talk, just use maybe lattice reduction as the secondary step to kind of make the attacks even stronger. And yeah, that's it for now. Thanks for your attention. I'm happy to take any questions.
Is there any question? I have one.
Yeah.
So for the side channel attack part, we see that there is a linear dependency between the number of traces required and the SNR. I guess if you were using two-share implementation masking, you would have a quadratic dependency. But what if, let's say, there is an implementation that is masking X, so it's C times S, but would not mask Y because somehow we think, okay, Y is just an ephemeral secret. How would be the, do you know how would be the dependency between the success rate and the noise? Or
I mean, we didn't run these experiments, but it kind of depends what kind of information you got on Y, right?
Yeah.
Because if you anyway get Y, then you don't really need to leakage on X, no? You can just exploit Y, and then you still have this linear dependency. So you kind of avoid the masking completely.
I mean, I was believing like in the belief propagation, the Y would not give the same kind of information during the combination, but.
Yeah, but I mean, we have like, I think we can also just exploit Y. So we don't really need all, like direct leakage on X.
Okay, so it would be the same, the dependency.
No, I mean, you have still less information, I think.
Yeah, there would be an offset, but it would still be linear.
Yeah,
probably.
I mean, you have to run the experiments. I can't say.
Any other question? Then I'll ask a second one.
Okay.
How much time does it take to process one attack trace? Is it very long with the BP algorithm on the lithium?
I don't know. I haven't implemented it.
Oh, yeah.
I just know that I think we had like, in our setup, we had like 2 GB of RAM. And that was already like too small for these sidechain attacks on rejected signatures without an earlier board. I think there we would need like 1 terabyte, which we don't have.
Okay.
But in terms of time, I don't know. Olivier ran it on the server.
Thank you. Well, if there's no other question, let's thank the speaker again. The next talk will be online, and one of the person on the paper is in the room, I mean the Zoom room, so we'll be able to take questions that will be answered in the chat. So the paper is about carrier fault, a fault propagation attack on sidechain protected LWE-based came. Yeah, I'm sorry if I'm mispronouncing the names, but the authors are Suparna Kundu, Siddhartha Chowdhury, C. Nyandip Saha, Anshuman Karmakar, sorry, Devdit Mukhopadhyay, and Ingrid Verboden. And the speaker is Suparna Kundu. Do we have a video or? They're having some issues finding the video, so they're trying to find it, and yeah.
Welcome everyone. I am Suparna Kundu and today I'll present our work, which is a fault attack on side channel secure implementation of lattice-based key encapsulation mechanism. I'll begin my talk with the current state of the art of post-quantum cryptography, where NIST has selected some post-quantum algorithms as standard and has published its first standard a few weeks ago. It has selected crystal Skybird as the key encapsulation mechanism or public key encryption standard, together with the three mentioned digital signature schemes. This work is focused on lattice-based encryption scheme, so we will focus on crystal Skybird in this talk. Now the standard has been selected and this will be deployed in the real-world cryptographic applications. Our real-world crypto systems are vulnerable against side channel attacks. This kind of attacks use physical information such as power consumption or electromagnetic radiation from the device during the execution of the cryptographic algorithm and retrieve the sensitive data. Point to be noted that all these schemes are mathematically secure and these attacks use implementation vulnerability of these schemes. One solution to prevent this kind of attacks is addition of masking techniques with the cryptographic algorithm. Now I will talk about how masking works. Here the first pair of pictures present an unmasked implementation. In this case, an adversary easily could find the secret value S by using side channel information. The second pair of pictures show the first order masked implementation of the previous implementation. Here, the sensitive data is split into two random shares and then we carry out the same operations on each of these shares separately. In this scenario, finding the secret value becomes hard. The decapsulation algorithm in any key encapsulation mechanism schemes is the most vulnerable operation against side channel attacks, as it uses the long-term secret key S. This picture shows the decapsulation algorithm of Kuiper. Here, first the decryption is performed, then the re-encryption is performed on the decrypted message, and finally the equality check is performed between the re-encrypted ciphertext and the public ciphertext. If it matches, then the algorithm outputs valid shared key. That means decryption success has happened. Otherwise, this algorithm will output an invalid shared key, which means decryption failure has happened. This algorithm mainly uses two kinds of operation. One is arithmetic operation, such as modular addition, modular multiplication, etc. And bitwise or Boolean operation, such as bitwise XOR, AND, OR, which are used in Keccak, and Keccak is used in XOR. Therefore, two kinds of masking techniques are used to mask the decapsulation algorithm efficiently. First is arithmetic masking for arithmetic operations, and the second is Boolean masking for Boolean operations. In these two kinds of masking, the sensitive data is split into two shares, and the modular sum of the shares is the unmasked variable for arithmetic masking, and XOR of the shares is the unmasked variable for the Boolean masking. Masked lattice-based algorithms are also uses masked conversion algorithm at some point to convert shares from one masking type to another masking type. The decapsulation algorithm of Kuiper after the integration of masking looks like this. Here arithmetic masking components are highlighted in blue and Boolean ones are in orange. Now we have several new components due to masking. These are the newly added components which are introduced the sake of masking. Several side channel attacks and fault attacks has been proposed on the implementation of lattice-based game. Several individual countermeasures has also been proposed. However, the real-world adversary is not limited to only a single type of attack, either side channel or fault attack. It can perform any feasible attack. The steps added for the sake of countering one kind of attack are those secure to another kind of attack or introducing another vulnerability. For example, the components added to counter the side channel attacks are those fault attacks secure. This kind of attacks is called cross attack, and it is one of the important steps to analyze and which is also the goal of this work. We found a fault attack that can exploit newly introduced components for masking in Kyber implementation. This is the masked encapsulation algorithm of Kyber. The fault attack location in this algorithm is the masked compress operation. This masked compress operation basically uses the arithmetic to Boolean conversion algorithm. This is the details of masked compress operation of Kyber. What this operation does, it takes two arithmetic shares and then performs some operations and change the shares from 3329 prime modulo field to 2 to the power 13 power of 2 modulo ring. Then perform arithmetic to Boolean conversion on the two arithmetic shares and finally extract the MSB from the Boolean shares and send it as output. The A to B conversion is the operation where we inject the fault. Now I'll explain the fault attack idea with a simple example. Here I changed the power of 2 ring size from 2 to the power 13 to 2 to the power 3 for simplicity. In this picture, x0 and x1 are the arithmetic shares of x and c0, c1 are Boolean shares of x. We have used stuck at 1 bit fault in this work, and we use the stuck at 1 fault at the 0th bit of x0, which is x00. The fault is active if the value of the x00 is 0, and if the fault is active, then it will always propagate to the 0th bit of c0 and c1. However, the active fault at x00 will only propagate to the first bit of c0 and c1 through carry. And it happens if the unmasked 0th bit of x is 1. Otherwise, the fault will not propagate to the first bit of c0 and c1. Similarly, the active fault at x00 will only propagate to the second bit of which is the most significant bit of c0 and c1 through carry if the unmasked 0th bit of x is 1 and the first bit of x is also 1. Otherwise, the fault will not propagate to the second bit of c0 and c1. In the end of the compress operation, only the MSB bit is extracted as the output. Therefore, the injected fault at x00 will only propagate to the M0, M1, that is the second bit of C0 and C1, if the fault is active and the 0th and the first bit of X are 1. Now, if we translate this result to the actual Kyber case, then we have to inject fault at 10th bit of X0. And if the fault is active, then it will propagate to M0 and M1. If 10th and 11th bit of the unmasked X are 1. 11th bit of X is 1. That is only possible when the unmasked message bit is also 1. The fault propagates to the message shares, means it will alter the message and will finally cause decryption failure, as the equality check between the re-encrypted ciphertext and the public ciphertext will not match. If the injected fault doesn't propagate, then decryption success will occur. It is possible when 10th bit of X is 0 with some probability, as injected fault might not be active if X010 is 1. Now the probability of the decryption success can be increased with the repetition of the same experiment. Now the decryption failure and success, each of them will give us an inequality with secret and error. We use them to retrieve the secret key S. We plan to use Giron's inequality solver to finally retrieve the secret key S. There was only one small hurdle, which is we observed decryption failure in 97% cases and decryption success in only 3% cases. The problem here is that the inequalities are not balanced here. And the inequality solver that uses belief propagation and with balanced inequality, it can converge to the correct secret key with high probability. But it was unable to converge to the correct secret key in our case. Therefore, we discard some decryption failure results to make the system of the inequality balanced. To be exact, we have discarded 50% of decryption failure results. Then the inequality solver returns the correct secret key for all the cases we have tested. We faced another problem during the experimental verification. In ideal case, we considered that the success rate of fault injection at the desired location is 100%. However, it is not the case in experimental setup. We observed the stuck at 1 bit fault at the desired X010 location only in 10% cases. In the remaining 90% cases, either we observed no fault or multi-bit fault at the least 8 bits of the shared X0. The good news is that although we do not get any useful information from these 90% cases, but these fault cases doesn't provide any wrong information to the solver with very high probability. Therefore, although there is noise in this experimental setup, but the noise is removable. Finally, we required 35K inequalities in total. In the experiment, we received 10% success rate. We required almost 70K different ciphertext, where we rejected 50% of the decryption failure results. We had to repeat our experiment in the cases of decryption success, maximum 180 times. On average, we had to repeat each cases 20 times, approximately. Total required fault injection was 1.9 million to retrieve the secret key of Kyber 512. In the right side, it is our experimental setup. It shows the probe position on the target ARM Cortex M4 board. In conclusion, we show a fault attack on the masked implementation of Kyber, and this attack is not limited to Kyber. Can be extended to any ring or module learning with errors or learning with rounding-based key encapsulation mechanism. We show our attack on Saber in the paper. Please check out for more details. Here we show our attack on the first order masked implementation of Kyber, but it can also be applied to higher order masked implementation of Kyber. The number of required fault injection in this case will be approximately same. Finally, we show that in the experiment with 10% successful fault at the desired location, we can break Kyber 512 with approximately 1.9 million faults. Please check out our paper for more details. For the future work, countermeasures against this kind of attacks are needed. Exploration of cross-attack locations will provide exploitable vulnerable locations, which will help to mitigate such attack locations. Finally, countermeasures against combined attacks is also one of the interesting future work direction. With this, I finish my talk. Thank you for your attention.